71, I'm meant to verify that a function is a solution to a differential equation, this thing here called the wave equation. And before I show you what it is I'm about to do, let me explain in more detail what a solution to a differential equation is in general. I've written out a quasi-definition. I'll explain why the quasi is on there in just a moment. Okay, a function is said to be a solution to a differential equation if substitution of the algebraic rule of correspondence of the function into the differential equation yields a true statement about functions. That is to say, for algebraic equations, solutions are ordered sets of numbers. For differential equations, solutions are functions. Okay, so a function is a solution to a differential equation under some circumstances, right? If when you substitute that function in, you get a true statement. Not a true statement about arithmetic, a true statement about functions. Okay, so what does a true statement about functions look like? A true statement about functions is, well, it boils down to what's called a trivial algebraic equation. Now, an algebraic equation in n variables is called trivial. This is a real definition if that equation is equivalent to the trivial equation 0 is equal to 0. Okay, you'll see an example of that soon enough. Let me address this quasi first. Quasi definition. Why is this not the full definition of a solution to a differential equation? Because not all functions are algebraically defined. Okay, so you could imagine a different situation where you have a function which is not algebraically defined, and nonetheless it serves as a solution to a differential equation because whatever substitution into the differential equation looks like, you still get a true statement. Okay. That's a rather abstract idea, but let's try to make these two things more concrete, all right? We're going to show that this really is a solution to this differential equation by substituting in this algebraic rule of correspondence into this differential equation and showing that we get a trivial algebraic statement. That is a true statement about functions. Okay, so because now I wish to substitute in this function for w. This will take a moment, so give me a minute to write in silence. I can't stand the silence. I might have to sing something. 2x plus 2ct and parentheses. Okay, good. Is equal to c squared. Now I'm going to have to use a slightly smaller font. d dx and begin parentheses sine x plus ct plus cosine. Why did I choose such a large function? 2x plus 2ct and parentheses. Oh, I just barely fit it on the page and did not fit it on the screen. At any rate, sorry it's not the most beautiful presentation, but this equation is equivalent to, not just implies, but is equivalent to. Right? This is an algebraic equation. Yes, it is an algebraic equation, even though it has the derivative operators, dt and ddx in it. It will be an algebraic equation in the end, and it was meant to think, we're meant to think of it as an equality of equations. An equality of functions. If the function over here is equal to a function over here, then this really is a solution to this. Now, I will calculate the first time derivative and leave the other time derivative operator sitting out there. The derivative of sine is cosine. And I need to use also the chain rule. Okay, so the derivative of cosine of something, the derivative of sine of something is cosine of something times the derivative of that something. Derivative with respect to t of x plus ct is c. Now that's all, okay? Plus, now the derivative of cosine is negative sine. I'll make a negative 1 right there. Sine. And a 2x plus 2 ct, and then I need to multiply by the derivative of the argument. That's the chain rule, so I'll need a 2c. 2c there. Okay, and on the other side, now I'm going to have to use a smaller font, c squared d dx, and then I will calculate the first of these derivatives. Let's see, I'll have a derivative of sine is cosine x plus ct, and then the chain rule, I need to multiply by the derivative with respect to x of the inside, and that is simply 1. So I don't have to write anything. I could say 1 times, but well, that doesn't change anything. Derivative of cosine is negative sine, and we have a 2x plus 2ct. Then I need to multiply by the derivative of the argument with respect to x, but that is 2 this time. We're derivative with respect to x, right? 2x plus 2ct, and no c appears over here. So we're getting c's from the time derivatives, but not c's from the x derivatives. Okay, the next t derivative, the derivative of cosine, will give me sine with a negative. And let's see, negative sine x plus ct, and then the derivative of the inside, so I'd get another factor of c, plus 2c, oh man, I should have said minus. Let's see, negative 2 c, and then the derivative with respect to t of sine is cosine 2x plus 2ct. And then I need to multiply by the derivative of the inside with respect to t, which is 2c again. So let's see, 2 squared here and a c squared there. Now, I still have that negative sign. Let's see. And then on the other side, pardon my alignment, I have c squared, and the x derivative will come out to negative sine of x plus ct minus 2 times derivative of sine is cosine 2x plus 2ct. And I need that parentheses right there. Okay, so I'm done with calculating all the derivatives. Do I have a true statement about functions here? Do I have a trivial algebraic expression? Let's see. I have negative c squared sine of x plus ct, and over here a c squared negative sine of x plus ct. Okay, so I could either slash this and this, but I don't like slashing. I think it's ugly. Or I can just remember that when I rewrite this, I'm not going to have that. Okay, let's see. It's equivalent to, and then I'll keep these two things. Negative 4 c squared cosine 2x plus 2ct. And then on the other side, right, so I'm getting rid of the signs on both sides. I have a negative 2 times, hey, wait a minute, did I forget the chain rule over here? Yeah, I did, right? When I took the derivative with respect to x, the second time I needed another one of those. Okay, so that's negative 2 squared, that's 4, and there's a c squared right there, and a cosine of exactly the same thing, plus 2ct, and that, in the end, is equivalent to 0 is equal to 0. Okay, so indeed, it was substitution of this algebraic rule of correspondence into this equation yields a true statement about functions. That is, it yields a trivial algebraic expression, and that is to say, for any numbers x and t that you put in to this function and to this function simultaneously, you'll yield a true statement about arithmetic. Okay, so that is to say that this function and this function really are equal. Okay, thanks for coming along that adventure, and I hope that you have a good sense of what a differential equation is now before you move on to a class entitled Differential Equations, where you will study lots and lots of differential equations, among them this one.